Here is a part 2 video of our relative velocity series, where on our previous video we looked at speed and velocity, and now we're going to look at relative velocity not only in terms of looking through at the specific magnitude based on our success criteria, but also the direction and looking at the plan for success. In this particular video, we need to remember the following. For relative velocity to be accomplished in terms of problem solving, we have the direction to be either equal to 90 degrees or 180 degrees. However, for the other part in this particular video specifically, we're going to be looking at where our angles is not equal to 90 degrees or 180 degrees. So that means there's nothing like, oh, just directly north, directly east, directly west, or directly south. None of those are going to be addressed in this video. Recognizing this actually introduces us to two strategies that will be helpful for we to be able to be successful in this video. And one here involves a strategy that some students use, which is called resultant. And in this case, we're not only looking at the x component, but also most importantly, we're looking at the y component. On the other hand, speaking of vectors, we are going to be looking at the other strategy, which is known as sum of vectors, or some people call it combination of vectors. And this here is going to be really an interesting strategy, and whichever one of these two works for you, go for it. Absolutely. There's a preferred one of mine. Is really short and straightforward, but it demands a little bit more of a really critical eye enough for you to be able to be successful in one of these two. So let's jump on to an instance, and this instance here is going to be based on a question that is as follows. A drone moves 320 kilometers per hour north, 45 degrees west, faces a wind that is moving at 67 kilometers per hour, moving in direction north 30 degrees east. Now determine the drone's resultant velocity relative to the ground level. For our solution blueprint, we're going to look at 4 different stages that will lead us to the final solution. And the first stage is in general diagram that has the different vectors in one particular graph, and then we're going to move on to the next step, which is a specific way of approaching the solutions. And this solution diagram, we will be looking at it in 2 fronts. One is involving our resultant x and y, and while the other solution diagram will be focusing on the combination vectors. And next is going to be determining the magnitude of our velocity, in this case the resultant velocity, for not only the first strategy but also the second strategy. And finally, we're going to determine the direction, in this case the angle that the resultant vector velocity makes relative to ground level. And this is how we're going to look at it. First, looking at the general diagram, and the general diagram here is going to be looking at it first in terms of having these coordinates that are designed right here. Take note that the one here is going to be noted as our north, and next is going to be here, which is east. This here is going to be south, and finally this here is going to be west. At this point, all these directions will be meeting at the 0 mark here, but take note that as you move from north to east and to south and west and back to north, you're making a round direction of 360 degrees. And so whichever way you start, some particular fields of study, they start from this line here and they make the round trip around, which is going counterclockwise. Some actually start here and move clockwise, some start at north, and for the purpose of this video we're going to start with the north, and based on the question, which is what we have right here, we're going to assign north as our beginning spot, and whichever direction that we go, that is pretty awesome. So for the drone moving at 320 kilometers per hour north, 45 degrees west, we can first determine where the line that is the vector for the drone is going to be pointing. In this case, since it is northwest, which is around this space, we are going to have our line to be drawn around that particular region. But now, how much direction is that going to be required? And in this case, it is going to be 45 degrees, which is not really accurate based on my drawing, but we're going to go with that. And so this is our 45 degrees for our specific drone, and the vector, which is the arrow, is going to start here and is going to be drawn all the way to a specific scale that is going to be a reflection a little bit of that particular vector, so, or in this case drone. So we're going to symbolize VD as our velocity for the drone. Now we have this for our drone. The next part here is the other vector, and the other vector is wind, that is going to be moving at 67 kilometers per hour north, 30 degrees east. And so in this particular general diagram, we need to determine where that particular wind velocity is going to be pointing, and in this case here, we're going to start off at north, and the direction is going to be, in this case, going towards east, and it's going to be 30 degrees. And so this is how much 30 degrees is. Although it's not really a great reflection, you will need a protractor to get that accurate, and the particular magnitude of our wind is going to be at that particular scale, which is a little bit smaller than that of the specific drone velocity. And so this here is going to be represented as VW. This is our general diagram for this particular question that is shown right here. Now we need to be able to predict, in this case, based on your understanding of combining velocities or vectors, what is going to be the resultant. If you notice here, as the drone is moving this way, we have our wind to be pushing it somewhere this direction. And so once you have that understood, you should be able to recognize that somewhere around this particular space or region, our specific resultant will be positioned. In this case, our drone relative to ground. So we need to be able to determine what VR is, but not only in terms of the magnitude, but also the direction. From our general diagram to now the solution diagram, we're going to look at the two strategies and compare how they stack up each other. And so once we have this generated for our general diagram, we're going to look at it based on first the resultant X and Y diagram. And in here, what we recognize is that we're going to look at two components. One component on the left side of this particular space will be dedicated to our drone, and while the other one here will be dedicated to the wind. And this is going to be important because we need to determine what the Y and X component here is and the X and Y component of here is, and once we're able to do that, we'll be able to move forward. First, for our drone, what we realize is that it's going to be focusing mainly on the northwest region, and looking at the northwest region as shown right here, we see that the vector is actually in that particular space. And so what we need to do is to be able to analyze this particular space. The angle here that is made is going to be 45 degrees, but most importantly, we know that if this is 45 degrees, this also as well will be 45 degrees. So introduce your x, and here is going to be the x particular component here, and the x component is going to be assigned as vdx, and while our y component here is going to be assigned the following. It's going to be assigned as our vdy, and we're going to relate these to not only the magnitude of our vd but also the angle, which is 45 degrees. Now we're done with the drone component. The other part here is the wind, which is going to be recognized as in the space of our northeast. And so we see that the vector is going to be pointing in that particular direction, and it's going to be symbolized as VW, and this here not only has its angle to be at 30 degrees for this particular space right here, but we recognize that the other space here is going to be more important, which in this case is going to be 60 degrees. And so once we have that, we can now introduce our x component, which is in the east direction, and this here is going to represent as vwx, and while for our y component we are going to represent it, which is pointing in the north direction, as our vwy. And once we're able to do that, we're going to relate our vw to that of our angle, which is 60 degrees, in order to determine not only what the y component is but also the x component. Next is looking at the combined vector, and for the combined vector we're not going to only use the particular component of our drone, specifically looking at the magnitude and direction of it, but also the magnitude and direction of the wind vector, and we're going to put them in one particular sketch. And here are a couple of things to keep in mind. First thing to keep in mind is that when we start with a specific vector, we have to introduce what we know as the coordinate, and this is going to be assigned for our drone. We need to show the vector for our drone, and this here is going to be pointing in that direction, 45 degrees. And once we have this established, our next part here is to be able to introduce our next particular vector, which is going to be starting at the head of our drone vector, and so that will be drawn right over here, and this is going to be assigned for or the start of our next vector, which is the wind vector, and this here is going to be pointing somewhere along the northeast direction, and this is going to be shown right over here. And remember that since it is 30 degrees here, we are going to look at it based on the inside space, which is going to be 60 degrees around this particular region. And remember that since we're looking at this particular Z pattern here, the angle here, which is 45 degrees, will also reflect here, which is 45 degrees, and we have this particular space to be taken care of for our angle combination between our wind vector and our drone vector, and that angle here is going to be 105 degrees. So remember also that the way to approach this is by connecting from head to tail, from the previous vector to the new vector. And once you're able to recognize that, we now can determine where the resultant vector is. And the resultant vector for this particular strategy is going to be still within the northwest space as shown right here. And take note, we have to start from the tail of our first vector and draw a line to the head of our second vector, which is the wind. And so we need to determine not only what this particular value is, which is the magnitude, but also the direction. Here is where we're going to move to the next step, which is to determine what the magnitude of our specific resultant x and y compared to that of the combined vector for this particular solution diagram. Now, to determine the magnitude, we're going to look at first the specific step for the resultant x and y. And what we're going to do is focusing first on the resultant y component. We see that the drone has is the VD to be multiplied by the sine of the angle, which is 45 degrees, and we're going to add to that of the wind's component on the x, and this is where the wind vector velocity is multiplied by the sine of the angle, which is 60 degrees. And so once we have this, we can now put in the variables where our VD is shown to be 320 kilometers per hour and our VW is equal to 67 kilometers per hour. You can put that into your calculator, and your value for your resultant on the y component is going to be equal to 284.297872 in the direction north. So this is something to keep in mind in terms of just keeping all the numbers, because we want to get the most accurate value for our answer. Now the next part here is looking at our V on the x component for the resultant. And what we have now is that, remember that for our drone, by conversion on the west end is going to be negative, and therefore we're going to have our negative VD to be multiplied by cos of 45 degrees. Don't forget the 45 degrees right here. And this will be plus our wind velocity multiplied by our cos of 60 degrees, 192.77417. Take note that it is a negative value, but this is negative. Negative reflects our west end, and this is going to be in the direction west. So once we have this, we are now going to combine these two vectors together for our resultant to get our final resultant. And what we see is that for this here, we have that to be the north direction for our y, and once we combine this to that of the x, which is what we have right over here, we're going to notice that our resultant is going to be in this direction, which is what we have right here from tail on our beginning vector to the head of our end vector, and this is in the direction of northwest. And therefore, once we have this addressed, we're going to recognize that yes, the VRY and our VRX is going to follow the Pythagorean theorem, and by so doing we'll be able to determine the scale of our specific resultant vector, which is represented as VR. Let's just put it that way, highlighted in blue, and we are going to determine using trig ratio to determine the angle, which is in this case the direction. So let's focus on the magnitude, and to find the magnitude through Pythagorean theorem, we should be able to see that the square root of our specific squares of the y component plus our square of our VRX, put that into your calculator, you should be able to get the final answer to be 343.49 kilometers per hour. And this here is actually taking into consideration the square root as well. So this is the magnitude here, and we're going to see how this is going to stand compared to this particular strategy here involving combined vectors. And for combined vectors, what we see is the following. We recognize that we are given the side, angle, and side. So side is in this case the drone vector, other side here is the wind vector, and we have the angle in between, which is 105 degrees. This angle faces the resultant, and therefore by using not the sine rule but the cosine rule, remember that this will be important in terms of being able to determine what the scale of our resultant is. And therefore by doing the cosine rule, recognizing that we're doing the side, angle, side, this is kind of something that I used to remember, that we have our VR to be equal to the square root, huge square root of our square of the vector of the drone plus the vector of the wind minus 2 multiplied by the vector of the drone multiplied by the vector of the wind cos of our angle, which in this case is 105 degrees. And once you put the specific numbers in here, we're going to get our VR, which is the resultant vector, to be equal to 343.49, which is amazing because it is identical or pretty much the same as this strategy right over here. So this is how these two strategies are compared to each other. One is kind of a longer method but pretty much fun and exciting, and while the other one is pretty much recognizing that we need to get the scales right and the angles right in order for we to arrive at this particular strategy to find the resultant vector scale in terms of the magnitude. Now we're done with determining the magnitude. We're going to look at our next step, which is determining the direction of the vectors in terms of how we're going to compare the first strategy with the second strategy. And to do that, these are the relevant information that we gathered from our previous step, and these are the following. One is that we're able to determine the resultants, which is not only the same for the first strategy but also the second strategy. But now for the direction, we need the relevant information, which includes the following. We're going to focus first on the first strategy, which is the resultant x and y's, and we need to find what this particular space is relative to the y, and this space is really important data. And this space here not only focuses on looking at this for our x to be the opposite, which is something to remember, but also looking at the other side, which is the adjacent. And this is going to be relevant because we are going to be using the trig ratios. Now why you might ask, is because this particular shape is known to be called a right angle triangle, as indicated right here. And so once we're able to do that, we're going to use a trig ratio, which is called the tan. And tan theta is looking at the ratio between the opposite and the adjacent, and we know that the opposite in this case is the magnitude of our resultant on the x component divided by the magnitude of our resultant y for the adjacent. And this here, once you do the inverse tan of this particular ratio, we should be able to determine what the final answer is. And to determine what the final answer is, what you do is that you put the numbers here into your calculator as shown, and our theta is equal to what? 34.1 degrees, which means that we see that this is north and this is west, and therefore our direction for this particular resultant is going to be expressed as north 34.1 degrees west for this particular resultant, which is our VR. This other strategy, all we have to do is recognize the following. Since we're given an angle, and this angle relates to the side which we already determined for the resultant, and we see here that, oh, we got an angle that we can find here. We can use those combination with a known side, which is in this case wind vector, to determine what a specific space is, and the space here is with respect to the resultant, where the resultant is laying in space. And to do that, we need to be able to determine what this particular angle is, which is called theta. And to determine what theta is, we need to first determine what this angle is as shown right over here. And this angle here we're going to label to be, let's say, alpha. And once you determine what alpha is, we will then proceed to finding what theta is. And to do this, all we have to do is develop a strategy which is called the sine rule. Of course, why? Is because we are not dealing with a right angle triangle, we're dealing with an obtuse angle. And so through the sine rule, we recognize that yes, our wind magnitude, which is represented as VW, is going to be divided by the sine of our alpha, because that is the angle facing the side, and this is equal to the resultant vector in terms of the magnitude divided by the sine of our angle, which is 105, which faces the resultant. And so once you have these, we are going to be able to solve for our alpha, and alpha we know is equal to 10.8599 degrees. Now remember that this alpha relates to this particular space, but we want theta, and to determine theta, all we have to do is do the following. We know that the full space here from our north all the way to the specific red line is 45 degrees, is the sum of our alpha and our theta. And so by performing our subtraction, we're going to arrive at our answer for theta to be equal to 34.14 degrees. And this is incredible as well, because it is exactly or pretty much identical to the one that we had on our previous strategy. And therefore, by placing it on our plane, we recognize that our vector resultant is going to be north 34 degrees west. And this is how we're able to determine the direction of the two strategies related to the question that we have right over here. So whichever strategy that works for you, either using this particular strategy called resultant X and Y, or using the combined vector, you are, with careful analysis, be able to determine the same answer no matter what. All the same, I hope you found this really informative. Go down into the comment section and let me know which strategy do you use or which one do you prefer. And I hope you found this really informative. All the same, stay smart as always and believe in yourselves.